Hello, everyone, and welcome to the Hyperthesis Podcast. My name is Patrick.
My name is Feely.
And I'm Liam.
And we have a special episode in store for you today, celebrating the two current physicists in the podcast. And the special reason is that we just had the Canadian Association of Physicists Congress, which is a Canada-wide physics conference that was held in Hamilton at McMaster University. So we'll be talking about that pretty shortly. But first we'll start, as we always do, to discuss some interesting topics that have come across us this past week.
I have an interesting topic. These things called Gross-Pidievsky triangular breathers. Now I'll break down what that means, but so I'm, again, I've mentioned I study these things called analog black holes in Bose-Einstein condensates. And this is a system of bosons. So it's a dilute gas of bosons. And what you do is you take this three-dimensional gas, so like in a box or something, and you kind of compress it down into a pancake. So you make it two-dimensional. And what you do is you kind of trap this configuration of bosons. So again, bosons, they're particles that can all occupy the same state, and usually they need to be very cold to do this. And by very cold, I mean usually around a couple Kelvin, sometimes micro Kelvin, or even nano Kelvin sometimes. But anyway, you have this 2D kind of pancake of bosons, and you kind of trap it in a certain shape. So you put walls around it so that it's in a triangle or a circle or a hexagon or whatever shape you want. And then you release the walls and put in a harmonic oscillator trap. So for the non-physicists, you can think of a kind of a weight on a spring oscillating up and down as a harmonic oscillator. When I say a harmonic oscillator trap, I basically mean just some kind of potential energy around these bosons that cause it to kind of oscillate. So when you remove this wall and put in this harmonic oscillator trap, essentially what happens is that whatever shape you start with, it expands outwards, and depending on what it is, it can reform into the original shape. And I don't know experimentally what caused them to try this. It seems kind of weird to me, but turns out a triangle, an equilateral triangle, when you release these triangular walls and put in the harmonic oscillator trap, expands outwards, creates some shapes, and then it reforms as an inverted equilateral triangle. And then it keeps doing this. It keeps reforming into a triangle, but flipped. So that's why it's called the triangular breather. And for whatever reason, it only happens with triangles and circles, but doesn't happen with squares or hexagons or anything else.
Well, this sounds like a lot of jargon. Even I was listening to it. It's like, what do you just say? Triangle flip and triangle expanding. So basically, it's a breathing effect, right? It's like expansion of triangle in size.
Yeah.
Okay, so you can see that in your BECs, basic BEC gas.
Yeah, I guess the simplest way to describe it is you just have this triangle wall, like this kind of walls that form an equilateral triangle with a bunch of particles in them. You remove the walls and apply some magnetic, electric field, whatever, and it breathes. It expands outwards and it reforms as a triangle, but kind of the directions flip. So it's rotated 180 degrees, I guess. And then it just keeps doing that.
So I'm curious about this only being held in a circle or triangular shape. I'm curious, have you seen if this has been done in experiment, or is this something that's purely theory? Because if it was done in an experiment, I'm curious if the type of atom used has an effect on it, because the type of atom in crystals, for example, affects the way that a crystal forms. So I'm curious if it's a similar situation where if it's a type of atom, it has, I don't know, threefold symmetry or something like that.
I don't think it has to do with the type of atom. It just has to be bosons. And I don't 100% know why that is. And the reason again, I don't fully understand why it's just a triangle and a circle, but it has something to do with Fourier space, which I won't get into because not a lot of people will understand. But somehow when you move into Fourier space, the equilateral triangle is a nice shape, and same with a circle, but all the other ones don't seem to be. So yeah, I think this was originally done in an experiment. Some experimentalists were just throwing shapes in and seeing what happened, and somehow an equilateral triangle gave an interesting result. So then some people did the theory for it. Yeah, so I'm studying, that's kind of one of my side projects right now, actually. I have an undergraduate student who works with me on it. So that's his project, and I'm just kind of there to help him out. And specifically, I'm studying at the edge of this triangle as it evolves. It's a shock wave, it turns out. So you have part of the wave moves faster than the speed of sound throughout the gas, and some of it doesn't. So that sounds very much like my analog black hole system. So I'm studying analog Hawking radiation in those shock waves as kind of my side project, which you can hear about in one of our previous recordings. Maybe the first one, I can't remember.
I think it was the first one, yeah.
Yeah, so that's kind of neat.
Yeah, I think since I've been in the conference all week long, there's so many interesting things that I can't even pick one. So I think, should we move on to the main topic?
Yeah, we could talk about that for a while.
Yeah, so I think let's start with conferences. What are conferences? Conferences for academia is basically where people go and basically present their results either in as oral talks or poster presentation, and start to network and get to know people, hopefully in your field, or maybe some people in other fields that might have applications for your work and such. It's a good, basically, social event plus academics event that you actually get to know people who do similar work and actually share some kind of familiarity to the field or to physics.
Yeah, and the nice thing about conferences is that they can be as broad or as specific as you want. So, for example, with the Canadian Association of Physicists, or CAP, Congress, that's any type of physics in general, and it can be even just remotely physics-based, and you can go and present and attend and meet other people who work in different areas and similar areas. Whereas there can also be very, very specific conferences that might have 50 people in them. I remember working with a master's student who studied some sort of sea life. I think they were called sea squirts, and he went to a conference and there were very few people there just because it's such a niche topic. And they range from industry to academics to a whole range of different situations and study areas.
Yeah, that's exactly what I was going to say, is that there's like some conference. There's a conference called Toucan, actually, which is kind of held, and it's the Toronto Ultra Cold Atom Network or something. So it's basically all the kind of Toronto region universities come together once every year and talk about their work. And like it's a fairly small conference, so all the sessions are held in the one after another in the same room, so everybody's in them together. That's not typical usually. So for CAP, it's such a broad conference that there's all these parallel sessions running at once. You kind of have to run around and pick and choose which ones you're going to go to.
I will also say about conferences, especially pre-COVID times and now becoming post-COVID times, as things open up, is that it gives you a great opportunity to travel the world too. So I haven't had too much experience with international conferences that have not been online, but there are conferences all over the world in every country imaginable. And even specific topics, such as, for example, remote sensing in forests, can be in very tropical locations. I attended a conference once. It was the Winter Nuclear and Particle Physics Conference run by the Triumph Institute in Canada, and that was in Banff. Would highly recommend, if you're a particle physicist, to check it out, because you get to go skiing for the conference. They allot time for that.
Well, and also as academias, like in your grant, your supervisor usually pay for conferences to a certain amount. Yeah, so there's some maybe you can go for free, right? And the registration for this conference can be as low as $50 or be as high as like $300 or $400. Can be ridiculous sometimes when you think about it. Just to walk around, listen to talks, but how the world runs.
I will add in that I've seen conferences well over $1,000 or $2,000, and I think I saw one that was over 10,000. But those are very specialized.
Yeah, I mean, I can believe it. Even at CAP this year, I mean, they in the hallway they'd have out all these like refreshments every like couple hours, and the amount of croissants I ate was, I don't want to say the number, it's embarrassing, but it might have been $400 worth.
Yeah, but also there are conferences that are aimed for like undergraduate or graduate students only. So those are relatively cheap. And it's where we usually go in our undergrad, right? For undergrad only it's just good to see other people in your program somewhere else, like compare courses and stuff.
Yeah, maybe we should talk about our experiences with conferences, because I mean, like Patrick was saying, he hasn't been to too many in person. Well, I don't know if he's been to any in person international ones, and I haven't either. So maybe we should talk about our experience with conferences, if you guys are into that. Yeah,
sure.
So I think our first experience with conference was at one called OPAC, which is the Atlantic Undergraduate
Physics and Astronomy
Conference, or something like that. Yeah, so that was the first conference I ever went to. Actually, no, it wasn't. It was CUPC, the Canadian Undergraduate Physics and Astronomy Conference.
Yeah, I think it's it's a CPC. I think that we went to first. I don't remember where. These are just like a few conferences we went to, and like we went to the same ones almost every year. CPC or UPAC, like it switched around, so we go to a bunch of those already.
So the first one I went to was in between the second and third year of our undergraduate degrees, when we did density functional theory, when we worked for that guy. So it was in Ottawa. Yeah, sorry, it was the beginning of our third year. It was in Ottawa, and it was CUPC, so it was the Canadian Undergraduate Physics Conference, which was really fun. I didn't present, but I think you did actually, Feely.
Yeah, it was at Carleton, if I remember correctly. Yeah, and what I presented there was so out there. It's super abstract. We didn't have any graph. We have equations, more equations, and more equations. It was rough. Like, try to explain anything at all. I can understand now that I do more computational work and something that's more visual that can actually show what's going on, like how we're solving this, and you can make like a lot more analogies, metaphors, and whatnot. But what we presented there was like, I think it was like ultra cold gas, where we try to use like semi-classical techniques on it, but actually just mathematical proof. It was fun to do, but tough to present.
Yeah, as an undergrad, you're new to all this stuff, so you tend not to really know what people want to see and what you should be doing. And the more I get into physics, the more I really appreciate hand waving at conferences, because you don't need to go through mathematical proofs in like a oral or poster presentation, especially when they're only like 10 minutes long. There's no time. I just want you to say like, here's what I'm talking about. Here's what I did. I don't need to tell you the details of it. If you want, you can talk to me later about it. And here's our result. So as an undergrad, you tend to not know that stuff, and you kind of struggle to, you trial and error, right? That's how you learn.
Yeah, I must say, at least in my experience, it's interesting to see the progression of being able to communicate these complex ideas. And I mean, that's what we're trying to do here even, is just science communication and distilling these very complex topics into something that's more digestible in about an hour. And that's what these conferences do too, is especially the general ones like CAP, where you have to take your research, which, like what Feely was saying about his past research, was just abstract, completely out there, and distilling that down into a 10-minute presentation and making it understandable and also interesting. So it's social, but it's also challenging to be able to communicate effectively.
And talk about science communication too. Like there are always those invited speaker that there for lectures, so that like some of them has two parts. Like first part like general public lectures, which are very little physics, but more like try to explain everything in like simpler terms for non-physics people to understand. And it's always interesting to compare when you go to both talks, where maybe it's a Nobel laureate talk and it's like it sounds super simple in the public talk, and then you go to the physics talk, they actually start to explain the actual theory of it and how they actually have to solve like million things to get their work done. And you can see the amount of omission in the information just to make the public understand that. To me, I know that how much work has to be put into it feels like, in the public it feels they make it a little too easy, but it's what needs to be done.
Yeah, it definitely needs to be done, right? It's like, at least, I can drive a car, but I don't need to really know how it works. And I think that's the same kind of idea with these public lectures, is that unless you're a physicist, like it doesn't matter to you. You just need to understand the overall kind of idea of it. And even like, so at CAP this year, I presented a poster, and I had to present to kind of 6 judges at one point in varying areas of physics. So like one could have been in medical physics, one could have did like condensed matter and so on. I had to present basically my last 3 years of research in 5 minutes to them. And if you listen to the first episode of the podcast, my area of research is very widespread. It's many branches of physics in one. So to explain it in 5 minutes to people who have no idea that it exists, it's definitely a challenge, but it's worthwhile. It's not just something you're doing for them. It's good for you to do as well.
Well, but it is certainly easier to explain to other physicists, right? Because your judges, even though they're in different fields, they have heard of, hopefully catastrophe theory or things you do a little bit. At least they heard of Bose-Einstein condensates.
Yeah.
They must have. If they're trained physicists, they should have. So at least when you actually try to explain to like your family or your general public, it's extremely difficult when you do something very advanced, like try to explain your stuff. Like that's why your first episode takes a while, right, to explain the theory leading to what you do. It's like, I think the same as Patrick and I, like we have to explain if we really want to get into what we do, like what I do, like what are statistical mechanics, what are those and why is it useful. And there's like another can of worm, because those are basically textbooks trying to justify themselves. And yeah, in terms of presentation in conference, and also it's nice to see how other people approach it. Some people really like go on the simpler and analogy method, while some people just go straight to the math, just no care.
Yeah, conferences are interesting in that regard because, if nothing else, they're a great learning experience, whether it's about a specific topic in physics or just seeing how people are able to present these ideas. So when they bring in invited speakers, it's most likely, I think I've only seen 1 or 2 throughout the past 6 or 7 years who really wasn't that great of a physics presenter, but all the other presenters have been well-spoken and they're able to communicate their ideas effectively. And they're more than happy to share their ideas, and even just watching their presentations, you can get ideas of, okay, this is how I can talk about this specific topic. So there's a lot of great learning opportunities at conferences specifically.
Yeah, a lot of the invited speakers have given basically the same talks like so many times. So imagine if you go to a talk of a Nobel laureate, what happens is that person probably flew around the world, give this talk 1,000 times already. Nevertheless, I always hear like people, even though invited speakers to give talk almost every week, still have to practice their talks all the time. So I don't feel bad about myself by having to practice 20 times before giving a 10-minute talk, because even the best people in the field had to practice like 20, 30 times to give like an hour long talk. Like, still.
Well, that's one of the reasons why they're probably the best, right? Is they put so much effort into what they do. Because I know that when I practice talks, the kind of outcome, what I want, the message I want to convey comes out a lot nicer than when I just kind of wing it, like I did at the beginning of this episode with the triangular breathers. That was a bit of a winging moment, but it turned out okay. So I have a question for you guys. How did you, I don't know if you attended any, but how did you feel about online conferences because of COVID? Because I attended a decent amount of them.
I've also attended a decent amount of them, and I've actually helped organize, I think, one. Yeah, and that was technically, I think it was the first virtual physics conference. So it was in June, so only a couple months after the pandemic started in Canada. And it's a different experience. As Feely said earlier, it's a very social experience, and you lose a lot of those social opportunities online. So I attended CAP online. I attended this virtual physics conference, which was out of Thompson Rivers University. And it was, you didn't get the same interactions. You still got to see the presentations, but again, they were all virtual, which meant you got to see the slides better, which was nice, and you could hear people. But at the same time, that's about the only benefit to having an online conference.
Yeah, so I attended some CAP conferences over the entirety of COVID and a couple other ones, and I also helped organize one, although it definitely wasn't immediately after COVID began. It was kind of near the tail end of it. And my kind of conclusions were that online conferences, like anything, there's good things and bad things about them. But I liked how kind of for smaller conferences of more tighter communities, like one specific area of research, like the sea squirts or whatever you were saying. If an online conference for that's good, because a smaller amount of people, that they kind of all know each other already, and they communicate very well. They can communicate effectively over Zoom, say. But I find for the larger conferences, especially when I was at them, there's like 200 people in the audience. There's no socializing happening, and it's very easy to just kind of minimize the tab and do your own thing and not really learn.
I like to say I begrudgingly hate online conferences or online any type of social interactions, because it just feels strange staring at the screen. But I've done so many of those in terms of socially. But I did help out with one of the conferences, and it's to me, there's a lot of hallway conversations missing. You present and you're gone. It's like you watch a YouTube video. It's like sounds kind of weird, but the truth was, at the time, I didn't have enough understanding of my results to actually present at any place at all. But now I feel pretty much better now. But yeah, that's my take on it.
Yeah, no, I completely agree. I like this in-person conference was great, especially you were visiting, so we got to catch up, and all the hallway conversations and going out for food and drinks after. That's where a lot of physics actually happens. Not so much like the math and stuff, but kind of the ideas and the connections and networking.
So since you were both just recently at a conference, the CAP Congress, why don't you catch me up on some of the interesting topics that you had?
Well, let me tell you about logarithmic catastrophes. No, I'm just kidding. That's my area of research. That'll be another time. Yeah, there was a whole bunch of stuff. I gotta think of one. You can go, Feely.
Yeah, well, this kind of relate-ish to my field. It's kind of another application-ish, because I was listening to talks on complex systems, but they use complex systems in ecology to try to basically understand why basically evolution happens the way it is and how things are connected in ecology. And I'm not really sure about these, because I don't research it. I just listen to like a half an hour talk on it. So I'm no expert, but we can use pretty much good techniques in physics, in statistical mechanics to also analyze this kind of ecological system. Because if you think of it, there are like enough, well, quote unquote particles, which could be living organisms, then they all interact in some way. They'll probably have some good, interesting results that came out, and which I don't understand very well.
I will just say that if you're curious to hear more about how we can apply different physics concepts and mathematical concepts to ecologies and ecosystems, go ahead and listen to a previous episode where I discuss my research.
Yeah, I think all the ones that are more that related-ish, that I understand a little bit more on the condensed matter field or solids, like basically material science, because those are super interesting. When you go on those talks, you will see like the actual like synthesization of material or stuff, and they always have pretty pictures to show, like, oh, this is how they build crystal and you can see it grows over time, or this is how they mix solids together and try to find, well, what if we mix 5 or 7 types of metal in one solid, and what is the property, what's the consequence of disorder in your system, and how to design a material with basically certain specifications that suit your goal, basically.
Nice. Yeah. So this conference, I tried to go to some talks that weren't in my immediate area because I want to kind of broaden my horizons a little. So I ended up going to this plasma physics talk, and I know very little about plasma, but it was talking about the northern lights actually, and how they're caused by ionization, I believe. Someone correct me if I'm wrong, but I think basically what happens is light and stuff comes from the sun. It kind of excites these particles in the atmosphere, and then after they're excited, they want to go down to their non-excited state. So the idea is that, I guess, if you have a ball on top of a hill, it rolls downwards and wants to go to the bottom. And when they jump from their excited to non-excited state, they emit light. And I think that's kind of the very, very basic idea of the northern lights.
Well, but I think plasma is different. Plasma are not excited states, right? They're basically electrons that, and the energy goes over the ionization energy, so it's released from the atom and to ions. That's what flames are. And I think that might be northern lights. I could be also wrong.
Yeah. I'm not 100% sure because, again, this was a talk out of my area, and they kind of just assumed I knew that when I went in, which is fine because, most of the people there are in that area. But basically, they were talking about how we don't even fully understand the northern lights. We have a good understanding of them, but there's these kind of other things that are more rare, other types of northern lights, I guess, that can happen. They're more rare. I forget what it was called now. But what they did is they kind of sent up this probe, and they actually sent it up on it might have been the first SpaceX rocket ship, because it was very cheap for them to do, because it was kind of, they're pushing boundaries. It wasn't like your typical space launch. So they sent up this kind of probe and measured like cross sections of what these kind of ionizing particles looked like, and they could determine properties of these rare form of northern lights. So there's all these different layers. So the Earth has its own magnetic field, and that shields the Earth itself from kind of all this radiation from the sun. A bunch of it, not all of it, but and there's different in different layers of these kind of this magnetic field, different things can happen.
I will just mention that there is a rarer type of northern lights, or aurora, called Steve. So I imagine they were talking about Steve, where, just as a bit of background, it was named as a joke by, I think they were amateur astronomers or something of the sort. They called these northern lights Steve, and it ended up being very significant scientifically, and the name Steve stuck. So we have aurora that are called Steve.
That's exactly the aurora they were looking at. And the guy told the story about how it was first observed by amateur astronomers, and they didn't know what to call it, so they joked about calling it Steve. And apparently, it's from the movie Over the Hedge or something. I don't really understand why, but he said that's what it was from. Could be wrong. The guy explaining it himself to the audience didn't know for sure. That he said that's what he thinks it was from. He heard it from someone and I heard it from him. So, like, you know, the telephone game, it's probably completely wrong, but who knows? Anyway, they actually assigned an acronym to it to keep it as Steve. So it actually stands for something now.
I will point out it was also discovered, I believe, in Canada. It was in Saskatchewan or Alberta. And Steve stands for Strong Thermal Emission Velocity Enhancement, just in case you were curious.
Yes, physicists are meme lords sometimes. They like to give funny names to things. Like there's these particles called machos, and there's one called wimps, and there's a whole bunch of stuff like that. But anyway, this talk was on that. So I went to that. My explanation of what I learned was very bad, but I enjoyed the talk a lot. I also went to a talk on the plasma in grapes, which we mentioned briefly before. And that was really cool to hear a second time, to see like what they've done since.
Well, one thing to point out too, that these conferences, the talks are very condensed. So we go into a room for a division, you're gonna have like probably 3 or 4 talks, one right after another, and you basically, you all of us here glass half full. And you feel too full, and you keep filling. So basically, it's like information overload, because you try to understand what happened in this talk, and then 10 minutes later, the next talk comes in, and maybe a little bit different in the same field, sometimes different field, and you just short circuit. You have too much information. You try to learn this, and then you try to learn the thing is similar to it, but it's quite different. So it's really interesting time. Like you get tired, like intellectually, mentally, but not physically.
Yeah, exactly. Like all the talks I listened to, I think I remembered like 2 to 3 key points from each of them. And the rest just goes in one ear and out the other, because you're there all day and you're just listening to so much physics, so much information. It's probably the same for other science conferences too. Like there's just overload of stuff. So for me, I tend to gain like a couple kind of tidbits of information here and there. And what's really useful, I find, by going to them is that if anything very interesting pops up, I write it down so I can kind of look into it later.
I will just shout out 2 people. I didn't attend CAP, but I did see a presentation that was part of my old collaboration. So first, I would like to shout out Liam for getting the first place in the poster presentation section. That's right? You received the first place for it?
So the way it works is that there's all these different divisions you can present in. So there's like medical physics and condensed matter, and I was theoretical physics, and I got first poster presentation in that, so thank you. I didn't get first overall, but someone at my university did, so that was cool. I got like 5th or 4th overall. The way they do it is they announce the top 3 overall, and then the 5th and 4th get an honorable mention. So I don't know which I was, but I'm going to pretend I was 4th.
And the second person I'll shout out is actually from my old group studying dark matter. It's Daniel Durnford, and he won first place overall. So out of all the presentations given at CAP, he won first for presenting the work that's being done by the new experiments with Sphere's gas dark matter detector that's currently undergoing trials and was previously installed at Snow Lab. So it's lots of good work going on there.
Good stuff, Daniel. I'd also like to do a shout out to our very own Feely. Very unfortunate circumstance. His oral presentation was, I'm not just saying this because you're my friend, but I genuinely think it was award winning. I loved it so much. I thought it was great. But so Feely, if you listen to, what was it, our 3rd episode, you study kind of complex networks in kind of military ships and other applications. It can be extended to other applications. But for whatever reason, the conference organizers lumped you in with the medical physics people. So of course your judges didn't vote for you because you weren't doing medical physics. But I genuinely think you had an award-winning presentation. It's just very unfortunate you were kind of lumped in with that division. But
thank you. That's very kind. But I'll take the L. You win some, you lose some.
Yeah, fair enough.
All right. The next topic, actually, to move on, I want to touch on the social aspect too, because we all, I think, growing up or watching TVs in any media, the physicists tends to be, the nerdy group, the crazy, or have these oddities to them. That's something very different. And I actually find some of it true, but most of it also not true. There actually a lot more diversity in physics. That we have incredible athletes in physics who are like top tier athletes, and they just it just not, doesn't fit the stereotypes that to say. I think the media perpetuate it so often.
Yeah, it's like the first thing I tell people, when I tell people I'm a physicist, the first thing they go on about, they either say, "Oh my God, I was so bad at math in high school," which I don't understand why they're telling me how bad they were at something. It's weird that people are just willingly racing to admit that. But anyway, the second thing they tell me is, "Oh, I love the Big Bang Theory. Are you like Sheldon?" And it's like, I've never fully watched the Big Bang Theory, but I've seen parts of it, and like, it's funny. Sometimes there's stuff happening on the TV, and I'm like, wow, that's literally my job.
Well, yeah, the TV, the Big Bang Theory is definitely a big, basically they publicize physicists, right? Which to me, I think is a good thing. Is a good way to get to know what we do and how complicated they are, and to get to that point, that to be able to understand those, you need a lot of knowledge. That's why, like, there are few people who do physics, and if you don't spend a lot of time reading or studying, it's really difficult to get into the field. And that's also comes to contribute to the stereotypes of physicists had to be reading books and stuff all the time, which is not in my experience, because I didn't like reading that much. To be honest, I just, try to find shortcuts to get through reading, which to me, it works pretty well. I like some books, I don't like some books, but if I don't like them, I try to understand them really quickly.
Yeah, I used to read a lot, but now that my job involves reading all day, I have very little desire to read when I get home. I just kind of want to play games or go out or whatever, right? But the Big Bang Theory does, I like it. I think it does a good job of kind of publicizing scientists in general, and it also, a fun fact, they had their own physicist on set who would like write all the math equations in the background. So all the math you see in that show is, I'm going to assume, is usually correct. So I think that's kind of neat.
Just another neat thing about the Big Bang Theory, and I think we learned this from Art McDonald, the Nobel laureate, but they have a scientist of the week there. So they'll have an actual, usually physicist, but a famous scientist come on set and get to watch the show from like a VIP seat. So it's not just the front end that we see that's kind of celebrating physics and science in general. They do it internally too, which is, it's nice to see.
Well, and also I think art is a form of, it can be satire. It points out absurdity in something, right? And of course, the absurdity in physics. A lot of physicists I met, including me, are the oddest people I ever met in my life. They have their own way of thinking, which, like, I just don't see that, that much in other fields. Like, they have, of course, other fields have some, but physics just has so many. Even you talk to faculty, like professors, you can tell, like, they're different. They're built different.
Yeah. Again, like, I can't speak much for other branches of science, although I have a lot of friends who are mathematicians and chemists and so on. But yeah, physics is this weird one because it's kind of, it's science, but it's also the most math heavy science. And I don't know if that just kind of breeds like different type people who are built differently, but
yeah, it's interesting because I've had experience in a lot of different fields like biology, chemistry, physics, and earth sciences. So it's interesting being inside and looking out, and then being on the outside looking in. And it's interesting to see how many people actually fit the stereotypes. So for those who may not study science or be in the sciences, each one kind of generally has a stereotype. So if you're a physicist, you're seen as like, as we've been talking about, different, not necessarily in a bad way, but you think differently. Whereas people in earth sciences are seen as like outdoorsy. Oh, let's go for a hike in our free time. And chemists might be a little bit crazy from what I've seen and heard. And it's interesting to see that generally people do have several aspects of the different stereotypes. But for the most part, people are a lot more multidimensional than that. And so seeing the different fields and comparing the stereotypes to the actual people, it's interesting to see where they fit and where they're different.
Yeah, like Feely was saying, you can have physicists who are kind of like, hunched over at a computer 24 hours a day like me. You can have like these athletic people who, you wouldn't look at them and say that's a scientist. And then one of my friends is a model who's a physicist, and they're dating the lead singer of a band. Like, you get all kinds of people, but deep down at their core, they are nerds. And that's what kind of makes them a scientist.
Well, even look at Liam, right? Liam is basically a quasi-professional bagpiper. No, I mean, you never know if you see Liam in an office, right? Then you see him in a kilt, like, oh, and probably your bandmates, first time meeting you, they think you're a physicist? Like, how many physicists bagpipe, you see?
Well, there was another physicist in my band, actually, as a drummer. But yeah, that's the only other kind of physicist I've ever met in the pipe band community. So yeah, it's not that common.
I also piped at one point. I haven't been with a band in a while, but there were at one point 2 physicist bagpipers in the same school.
Yeah, the odds of that are almost none. So I always thought that was fun. You had to play more. We didn't jam very much. It broke my heart.
One day.
Yeah, there are also a lot of physicists who play hard. Like, it's not like we sat around all day and then go home and sleep. Some people go out to bars and drinks, have fun, or patrons of the arts. There are actually like a lot of social aspect to physicists. It's kind of fun, actually. We are like because like I don't like to talk about work outside of work, but the conversations always end up like having something to do with physics, or we put examples in physics to make fun of things or to relate things to one another. Yeah, and it's nice to be able to basically put your knowledge at work to socialize, basically.
Yeah, I like how you said some people like to go out and party. Some people. I wonder who these people are. But yes, I completely agree. We are running out of time, so I think we should kind of move on to our final topic of our... Oh, Patrick, what do you got to say first?
Just before we move on to our final topic, as always, right before you hear a nice little story, this time from Liam, we wanted to let you know how you can reach us and where you can listen to us. So you can find us mainly through anchor.fm/hyperthesis, and that's where our podcast is hosted. However, we all are also on Spotify, Apple Music, Google Podcast, and we're working on getting to more places where you can listen to podcasts, so we're accessible to as many people as possible. If you have any questions for us or any comments, any suggestions, or if you'd like to perhaps one day speak and be a guest on this podcast, please either contact us through our Instagram at Hyperthesis Podcast, or you can reach us out to our email, and that's hyperthesispodcast@gmail.com. So feel free to reach out with comments, concerns, queries, questions, anything you like, and just give us a follow on Instagram too.
So back to Liam. So I think today Liam's going to be introducing us to the concepts and history and the intricacies of rainbows. Take it away, Liam.
So I want to make one of our podcast discussions in the future. I just want the main topic to be rainbows, because I could go on about that for a couple hours. But today I'm going to go through a very short kind of history of rainbows and some very basic concepts, like what is a rainbow. So rainbows are basically the kind of scattering of white light. So white light comes in from the sun. It refracts in these water droplets, so rain. So you can think of a water droplet as a sphere, and light kind of bends as it enters a different medium. That's called refraction. So it enters this water droplet, it refracts, and then it reflects off of it on the inside and bounces out. And that happens with a whole bunch of raindrops, and you get rainbows basically because different colors of light disperse as they refract. So white light enters the raindrop, and it kind of gets split apart into different colors. The colors of the rainbow, Roy G. Biv, is the way I remembered. So red, orange, yellow, green, blue, indigo, and violet. And that's what you see. So that's kind of like basically what a rainbow is. And it turns out there's different orders of rainbows. So when the light enters when the light enters these water droplets, it can go straight through, but some of it refracts and reflects once. So it refracts once and then comes out, and that's called a 0th order. It goes in, it refracts, and then comes out the other side, and that's a 0th order rainbow. The rainbows that you usually see when you think of a rainbow, like that big kind of arc of all the different colors, is a 1st order rainbow. So that it goes in, it refracts, and then it bounces out. And then there's 2nd order rainbows. It turns out when you see a double rainbow, that second one on the top, that fainter one, is a 2nd order rainbow. And then there's 3rd, 4th, 5th, and so on. And anything 3rd order up is very hard to see. I think in nature we've seen 3rd, 4th, and 5th orders, but they're extremely difficult. You need the perfect conditions and the perfect raindrops. So kind of a history. Back in the 3rd to 2nd centuries BC, this guy named Alexander of Aphrodisias, or Aphrodisias or something. I'm pronouncing it horribly wrong. I'm sorry. Basically, an ancient Greek philosopher named Alexander was kind of one of the first people to sit down and try and understand a rainbow. And he knew it was some kind of phenomenon that involved light and color. But he believed rainbows were composed of 3 colors, red, green, and blue, and that all the other colors you see in a rainbow were kind of combinations of these. And that was probably more from like an art theory point of view. When you mix colors on like different colors of paint, you get other different colors. That's probably where he was coming from. And he also believed that... He also believed that it wasn't just a kind of a physical effect. It was something to do with our senses. So why we saw the colors we do. And, technically it is because we can only see certain wavelengths of light. But rainbows are kind of a physical phenomenon, which I'll come to.
But yeah, just to point out, the RGB, if you do photography and stuff, like, is a mixing up lights when you do lighting and stuff. But the toners people use in like paper or printing, it's actually CMYK. It's a cyan, magenta, yellow, and black. Don't ask me why. I have no idea.
Yeah, so you can create different colors by mixing these. They're different color schemes. So back in, the 3rd to 2nd centuries BC, this guy thought it was red, green, and blue, and that it was both a physical and a sensory effect. Aristotle, much later in around 300 BC, who was also a Greek philosopher, he was the first to give a more complete description of it as an optical phenomenon. So he went out and he observed rainbows and he cataloged all these different types and what they looked like at different times in the day and different parts of the year. And he came up with the conclusion that rainbows at most appear in 2s, so a double rainbow. And he also noticed this very dark band in between the 2 rainbows. So if you see a double rainbow, you notice that in between them is very dark, and this is called Alexander's band, and that's named after the original Alexander I just talked about. And he predicted that there's only 2 orders, but like I mentioned, there's more than that, and we've seen them now. But you need very good conditions to see them. So his kind of description of rainbows had a lot of flaws, but it was quite good for the time, and it was for most rainbows you see, it was pretty solid, and it remained unmatched for centuries. So for about 300, 400 years until around 4 BC to 60 AD, this guy named Lucius Seneca, and I'm again probably pronouncing that wrong, was a Roman philosopher. And he was the first to suggest that rainbows, which always appeared opposite to the sun, were created by the reflection of sun rays on water droplets, which he's getting there. It's pretty close. Because he noticed one day that it was possible to see a rainbow when light passed through a glass cylinder. So he kind of made this connection that what you always see a rainbow on the opposite, where if the sun's behind you, you're going to see a rainbow in front of you. It always appears opposite to the sun when in raining conditions. So he made that connection. So that was another step. And for hundreds of years, all these different kinds of scientists, I can't go through all of them, there's hundreds, but they all tried from all around the world to understand rainbows. So rainbows are a very old kind of scientific endeavor, which I think is really cool, and how my research is connected to them like that. So we owe, I know it's horribly pronounced, Willebrord Snell. It's probably pronounced like Willebrord Snell or something like that, but a Dutch astronomer and mathematician who people who've studied physics will know for Snell's law of refraction. So when light enters a different medium, it gets bent by some angle. He was the first to kind of come up with the fact that he made the connection to his law of refraction that rainbows should be strictly physical phenomenon. So it shouldn't depend on kind of sensory things. It's not some kind of illusion to do with your eyes or the way your brain perceives it. I mean, it is in the sense that, the light enters your eyes, hits your retina, and you send a signal to your brain. But you're not seeing it there because of your brain. If you were to put out these kind of detection devices, they would measure the rainbow to be as we see it, roughly. So he came up with that, and later, in around the 1600s, our the best boy, Isaac Newton, English physicist and mathematician, he did his famous prism experiment, which told you that different wavelengths of light refract differently. So he had a little, as a hermit, he kind of like isolated himself in his room. He made a little hole in a curtain or something like that. A single beam of light came in and he held up a prism and it split that white light into different colors, the colors of the rainbow. So he came up with this connection that each sun ray kind of generates its own rainbow. And that helped lead to the understanding that all the colors in a rainbow are just white light being kind of split apart by the raindrops. So the reason why I think rainbows are really cool is because it turns out there's a thing called caustics, which if you listen to the first episode, I talked about in a good amount of detail. Caustics are basically the natural focusing of rays or waves, and rainbows are specifically two rays of light being focused together. So when your light comes into your raindrop, it comes in at a whole bunch of locations in the drop, it all reflects and refracts and so on. And what you see, the colors, each color of a rainbow is two rays being focused together into your eye. So I study those because caustics are kind of described by this thing called catastrophe theory, and I won't get into that because I've talked about it before. But there's all these different kinds of rainbows, not just the ones you see. There are rainbows that appear in fog. They don't have to appear in raindrops. There's like different kinds. There's things called corona, which aren't quite a rainbow. I could go on all day, and I want to talk about this in a future episode. But there's still a few mysteries with rainbows, but for your typical kind of rainbows you don't have to search too hard for, there was still one mystery left after all these thousands of years of scientists trying to understand them. And they were known as supernumerary rainbows. So when you see a rainbow, you see the primary bow, and then you'll sometimes see a double rainbow. But in certain conditions where your raindrops are sufficiently small, you'll see what appears to be kind of a series of smaller, dimmer rainbows below the primary bow. And those are known as supernumerary rainbows, and they cannot be described by geometrical optics. So all these people, Newton, Snell, Alexander, they didn't know about kind of the wave nature of light. They were thinking in terms of rays. which is a good approximation. But if you want to understand these smaller supernumerary bows, you need to treat light as a wave. So the fact that waves interfere. So when you kind of splash in the water, it'll create a wave. And if you create a splash somewhere else, the waves will kind of overlap with one each other and amplify, or they'll deconstructively interfere and kind of cancel each other out as they pass through one another. So by taking into account the interference of light, a man known as George Bedell Airy was able to properly describe these supernumerary bows. And turns out they depend, like I said, on the size of the water droplets. So you need all these water droplets to be small and all of them to be near the same size of one another. And that's where the Airy function came from, which is a very famous function in physics. So that's kind of like the basic history of rainbows. People still study them now, but they mostly study these kind of higher order rainbows and some other rainbow-like phenomenon, which have some mysteries around them, which I wish I knew about, but maybe I'll talk about that in a future podcast after looking into it. So yeah.
All right. Thank you, Liam, for the enlightening story of Rainbow. And it looks like we're running out of time. So, well, on that note, I'll see you guys next week.
We'll
Bye,
see you
everyone.
then.